When you look at a $1 billion fighter jet or some cutting-edge tactical vehicle, right, you think about the engines, the armor, the crazy advanced sensors. But what about the simplest component of all? The humble ground connection. It's so easy to overlook, but a single failed bond can literally be the difference between mission success and catastrophic failure. Okay, let's dive into this unsung hero of modern engineering.
This quote from our source material, it just says it all, doesn't it? We are not just talking about some A-plus engineering practice here. No, no. In the world of aerospace and defense, proper grounding, or earthing as it's often called, is a fundamental requirement for the machine to even work, let alone survive in a really hostile environment.
So, what are we even talking about when we say grounding in a vehicle? Because it is so much more than just a wire running back to a battery. It's an entire engineered system that uses the vehicle's own structure in a really, really clever way.
Okay, so here's the genius part. Instead of running these super heavy copper return wires for every single light, radio, and motor, engineers just use the metal airframe or the chassis itself as the return path. I mean, think about it. This saves a ton of weight, which, as you know, is absolutely critical for performance and fuel efficiency. The entire machine becomes an integral part of its own electrical circuit. But this whole structural ground thing, it isn't just one big free-for-all. It's actually made up of two distinct but interconnected networks, and each one has a very specific job. The easiest way to think about it is like a power superhighway and an electrical safety net, and they're both working together.
All right, let's break this down. First, you've got the Electrical Structural Network, or the ESN. That's your superhighway. It's built to handle the heavy traffic, all the high current returns from big motors and powerful systems. It's also what safely channels these huge energy spikes from things like a lightning strike. Then you've got the Metallic Bonding Network, or MBN. This is the safety net. Its whole job is to make sure every single piece of metal on the vehicle is at the exact same voltage. Why? To prevent dangerous static sparks that could, ignite fuel vapor. Okay, so we've got this really sophisticated network, but why is it so vital? Well, the source material kind of boils it down to what you could call a rule of three. Three mission-critical functions that protect the people, the equipment, and the data. First up, clean and simple, safety. A bad ground can turn the metal case of any piece of equipment live, and that's a serious shock hazard. Second, it's about fighting electronic noise. I mean, in a modern military environment with countless signals flying around, proper grounding is what lets shielded cables do their job and protect sensitive electronics. And finally, reliability. Your fancy, expensive sensors are totally useless if their ground reference is floating all over the place. That leads to corrupted data, and that leads to bad decisions. And you have to understand, the electrical environment these systems live in is absolutely brutal. According to the military standard MIL-STID 1275, a ground vehicle's 28-volt system has to be tough enough to withstand repeated voltage spikes of up to 100 volts. The grounding system is the #1 defense, shunting all that dangerous energy away before it can fry the electronics. But our unsung hero isn't invincible. Over time, there are these insidious forces, the villains of our story, if you will, that are constantly working to degrade and destroy this critical network. And these failures are often slow, they're progressive, and they're incredibly difficult to find. So first up is the ground loop. It's basically an unwanted electrical detour. Imagine a high-power motor and a super-sensitive sensor are both grounded to the chassis, but at different spots. When that motor kicks on, it causes a tiny voltage difference between those 2 points. Well, to the sensitive sensor, that small difference is like someone shouting in its ear. It completely corrupts the signal, making the data totally useless. In this slide, wow, this illustrates another huge enemy, galvanic corrosion. When you put two different metals together, say a copper lug on an aluminum frame, you basically create a tiny battery as soon as you add a little bit of moisture. And this process corrodes the connection, creating this non-conductive oxide layer that just slowly increases resistance until the ground fails completely. And then you've got arc faults. A parallel arc, that's a direct short to ground, is loud and obvious. The current spikes, and poof, the breaker trips. But a series arc fault, that's the real silent killer. It's caused by just a loose connection. The current doesn't increase, so the breaker never trips. Instead, that arc just sits there, generating thousands of degrees of heat, melting wires and eventually starting fires. So how on earth do you find these tiny developing failures? Well, you can't just use a standard multimeter. Its own wires have too much resistance. So technicians use this special 4-wire method called Kelvin testing. Two wires inject a very precise current, and then two completely separate wires measure the voltage drop. This lets them measure incredibly small resistances with extreme accuracy. And the level of precision they are looking for is just staggering. For a critical piece of avionics, the maximum allowable resistance for its ground bond is just 0.003 of an ohm. That is an incredibly small, almost impossibly small target to hit and maintain over the entire life of an aircraft.
So, we've established the stakes are incredibly high and the tolerances are razor thin. But just as engineers have mastered grounding on metal vehicles, well, the game is changing. New materials are introducing entirely new challenges, making our unsung heroes' job even harder.
Yeah, the biggest shift right now is the move to carbon fiber composites. See, an aluminum airframe is a natural, built-in ground plane. But carbon fiber, it's a really poor conductor. So all of a sudden, that free structural ground that engineers have relied on for decades is just gone. They now have to build an artificial one from scratch, embedding these complex copper grids throughout the whole structure, which adds weight and a ton of complexity.
So, this is the crucial point we're left with, this fundamental challenge. As our most advanced machines are being built from what are essentially non-conductive materials, and at the same time their internal power demands are skyrocketing, engineers are faced with this fascinating and absolutely mission-critical question. How do you ground a system that, by its very nature, has no ground? Answering that, well, that's the key to the next generation of aerospace and defense.